We begin our discussion of Chapter 3 by introducing a definition of a random variable. The random variable is the way that we represent an event in analytical form. In Chapter 2, we had a lot of Venn diagrams and we discussed our sample space and events occurring within the sample space, but we did it graphically to represent analytical events. In order to apply mathematics to these types of problems that we're discussing, we need to introduce a random variable. So if x is a random variable, then we can take on values of x equal to lowercase x. X could be less than some value, take on values less than some value, lowercase x. Or our random variable x could take on values that are greater than some value x. So this could all represent an event where x may be between a and b, values of a and b. So the notation here gets a little tricky in the textbook. They use uppercase x to represent what random variable is being discussed. And then they use the same letter, but the lowercase, in this case x, to represent what are the possible values that x can take on. So keep that in mind. It is a little confusing, but that's the notation that the book has adopted, and we will do the same. So we map a random variable onto our real number line. So in Chapter 2, we discussed problems that had similar drawings to what we have here at the top of the slide, where we have some sample space S, and we have a couple of events occurring in the sample space. There's a little bit of an overlap or an intersection, and then we have the complementary event, or the union of the complementary, the complement of the union of the events, represented in the white areas. So if we want to do this in analytical form, if we want to discuss this in analytical form, we need to map this sample space and these events through our random variables, and we do that simply by saying, well, okay, if this is event number 1, let's say we can represent it on our real number line x, because x is going to, lowercase x is going to take on our values. We could say that event 1 can take on values that are less than or equal to b, but greater than a. So event 1 would have numeric values in this range in here. Event 2, likewise, we could say can take on values that are less than d, less than or equal to d, and greater than c. So event 2 could be represented by this range on the real number line. Our complement of our union, so remember our union is the footprint of these two events, and the complement is everything that's not the footprint, so the white area here. So the complement of the union, E1, E2, is going to be, on our real number line, the random variable x taking on values that are less than or equal to a, in addition to the random variable x taking on values that are greater than d. So that is going to be everything that is below a and above d. Equal to, below or equal to a, but above d. And finally, the intersection or the overlap, E1, E2. Remember the notation that we've adopted in the textbook. We dropped the intersection symbol and just put in the E1, E2 notation here like this, is going to be equal to that intersection, or x, the random variable x can take on values that are less than or equal to b or greater than c. So everything in this range right here. Now in order to describe what the values of x are going to be, we assign them a probability. So we give values of x are given a probability through the use of two types of functions. And the functions can be either discrete, and this is where the values of x, our random variable, is defined by a set of finite values. So they're discrete values. Let's say they're 1, 2, 3, 4, 5. That set of 1 through 5 is a discrete set. The function can also, or it could be continuous. In continuous, the values are defined by a continuous function. In that case, as you know, a continuous function can take on any value, so there's really an infinite number of possibilities even within a range. We can take a subset of that infinite set and we'll still have an infinite value because we can take on, let's say, 1.1, 1.11, 1.11111, and so on. So we can have an infinite number of possible values, albeit within a specified range if we so desire. But continuous, so there can be the function that describes the probabilities is continuous. So let's start with describing what these probabilities are with what's called a cumulative distribution function, or CDF for short. So this is, I'll often refer to this simply as the CDF. So the notation for CDF is f sub x. So this is uppercase x, uppercase f, and an uppercase x. So your book uses this as the CDF, or the cumulative distribution function, of the random variable x. So what this is equal to is simply the probability, and we've seen this notation before, capital P with parentheses, that represents the probability. The probability that the random variable x will take on values less than or equal to lowercase x, some value, for all values of x. So this is kind of a descriptive way that we define what our CDF is, or our cumulative distribution function. So for a discrete random variable where we have our number line down here, x, the values of x, and we have maybe the discrete values of x1, x2, 3, 4, 5, 6, and so on. And then we have what is the CDF on the y-axis right here. So a CDF is simply the plot of all of these values and the probability as we get to that value, but adding to it the sum of all the previous probabilities. So at x1 we have some probability for x1, and then when we get to x2 we have the probability of x2, and we add to that the probability of x1, and we keep on going until we get all the way to through our set. And notice that once we reach the end of our set, the CDF value is equal to 1. So this is our sample space, because we have now exhausted all of the values that x can take for a discrete random variable, and we've gone through each one, and we have finally gotten to all through our sample space, and we reach 1. Recall that the area of the sample space is equal to 1. For a continuous random variable, again we have our x, our number line x, and we plot against that the CDF, and it may look something like this. There are a multitude of different shapes for different functions that we'll define, we'll see, but this is a good example where we have a ramp up to an asymptotically shape, and then ultimately when we get to in many cases plus infinity, we will reach 1, the probability of 1. So this again defines all of our sample space, but in a continuous fashion where there's not this step to it, but we have a smooth transition as we go from 0 all the way up to 1 for a continuous random variable. Now let's take into account the discrete random variable first. So another way to describe a discrete random variable is through what's called a probability mass function, or PMF. This tells us the probability of our random variable taking on a specific or discrete value. So that previous CDF had x1, 2, 3, 4, 5, 6. Well, each of the individual, if we plot up each of the individual probabilities rather than their sum, what we're plotting up is the PMF. And the PMF, your textbook uses the following notation: the lowercase p of subscripted uppercase x to represent what the random variate is, of x sub I. Because remember, what we're really describing is the probability that the random variable x will take on a specific value, let's say x sub I. So this is the notation that they use. So just by our simple discussion so far, you can probably guess that the PMF and the CDF are related. So for the discrete case, recall that our CDF looked like this. We had this step function where each of the previous probabilities that it takes on a value gets added, and then we ultimately end up with probability of 1 once we go through our set. Well, for the PMF, each of the individual probabilities is simply plotted up, not the sum of them. This is the PMF, or probability mass function. And if we were to simply sum all of these up as we go, then guess what? We get the CDF. Okay, so the CDF, remember, uppercase F, uppercase X representing the CDF of the random variate X, is equal to the sum of all is equal to the sum of the probabilities that the random variable X takes on a value equal to x sub I for all the x sub i's less than or equal to the whole sample space, or the whole, every single value that the random variable can take on x. And this, in the book's notation, is simply equal to, again, the sum over all the x's of the PMF of x, the random variable x, taking on the values x sub I for all the x sub i's. So the CDF is nothing more than we simply summing these up as we go. But the PMF is the individual probabilities for what they're taking on. At this point, take a look at example 3.1 in the text and review the video that is posted for example 3.1. Now, if x, or a random variable, is continuous, we define instead a probability density function, a PDF. This tells us the probability is in the range of A, B, between A and B. And notice how the notation is here. We've got a parentheses around A and a bracket next to B. This means it includes the value B, and this means that it goes up to but not including A. So for a continuous random variable, we define a probability density function that tells us the probability that the random variable x will take on a value that is less than or equal to b but greater than a is going to be equal to the integral from a to b of this function f, and this is scripted lowercase f, sub x, where this is our random variable, of x, the values that it could take on, dx. This describes the function as a smooth, continuous function. The PDF describes the density of probabilities. So for the PDF, we don't say, well, what's the probability that x will take on a value x sub I? We don't say that. That's a discrete question. It's not a continuous question. A discrete question does ask that. What's the probability that x can be value x sub I? That's a PMF answers that question. A PDF, we have to think differently. We have to think in terms of a density. because it doesn't give us a discrete value. It gives us the density where the probabilities are greatest. So in this case, the probabilities are greatest in this area here. So there's a higher probability that values will be in this range, in here, than they would be over in this range, or in this range. So a PDF, we have to describe it in terms of a range. So we assign it a value. We say, typically what we will say is, what's the probability that x is less than or equal to 1? Right? Now similarly, how we could derive the CDF using the PDF, well, the relationship is similar in a continuous function as well. The CDF for our continuous function, or for our continuous random variable x, is equal to the probability that x, random variable, is less than or equal to x. This is equal to the integral from minus infinity up to the value x that we're interested in of fx, and in this case we don't want to confuse this this x with this x up to a certain value, is, let's just say, tau d tau, where this describes what is our probability density function look like. Right, so we take the integral. If we are interested, let's say if this is the value x that they're talking about in this, if this is the value x, then the probability density function would give us, this integral would give us all the probabilities from this value down, the sum of all of these. That's equal to the CDF at that value. Right, so we could, they are related. We simply take the integral from minus infinity up to that value to get what is the CDF value. So the PDF is related to the CDF, much like the PMF is related to the CDF. Now, if our CDF, fx of x, has a first derivative, then the PDF, we can go in the other direction as well. We can get from the CDF, we can get to the PDF. We simply take the first derivative of the CDF. So our PDF, fx of x, is equal to the derivative of our CDF, fx of x dx. So we simply take the derivative. If we're given a continuous function for our CDF, we take the derivative of that to get what is our PDF. So we can go back and forth in that case. Now there are some rules for any CDF. The first one is that at a value of minus infinity, it has to be equal to 0. And at a value of plus infinity, it has to be equal to 1. So the CDFs go from 0 to 1. So a function, you can't just make up willy-nilly a function and say it's going to be a CDF. It has to follow these rules, and the first two are the most important, or the first two are what really are going to bound this. We're bounded by 0 on the low side and 1 on the high side. So this really is describing, again, all of our sample space, because when we have no values of x or no events that we're trying to analyze, then we have no probability and we have no footprint in our sample space, so it's equal to 0. If we have all the possible outcomes, then we've exhausted our sample space, so we're at plus infinity in the terms of a CDF. We're at plus infinity, so we're equal to 1. We've exhausted the entire sample space. Additionally, fx of x for values greater than or equal to 0 must have values greater than or equal to 0 for all values of x. Right? We cannot have a CDF value that is less than 0. Cannot be. The CDF is non-decreasing, so it must always increase. As we go on our number line from our values x, x sub I plus 1, and so on and so forth, all the way up to the end of our sample set, it has to be increasing. The CDF has to continue to increase. It rises. We saw that in the two examples, the two drawings on the previous slides of our CDFs. The discrete one, we had that step function. It was going from 0 up to 1. And for the continuous function, again, we're going from 0 to 1, from minus infinity to plus infinity. The CDF is continuous to the right of x. So it must be continuous. It cannot be it cannot have start and stops. So by that I mean it cannot be discontinuous. So the easiest way is probably to draw this on the slide here. So if we say this is our CDF, we cannot have a discontinuous function. So it cannot look like this, where we have continuous or even stepped up to this point, and then it's undefined for this region, and then continues to be defined for additional values of x. This is unacceptable. We cannot have this for our CDF. So these rules are important to keep in mind, because any function that follows these rules can be a certified CDF. So we can calculate the probabilities that the random variable x will take on values, let's say, less than or equal to b, but greater than a, by use of the CDF. So we take the PMF, or the PDF in this case, for a continuous random variable. We take the PDF, and we say that the f of x dx from minus infinity to b, and we take that value and we subtract off the integral of the PDF of x, f of x dx from minus infinity to a. We subtract that off of this value, and we end up with the probability that our random variable x will take on this range. For a discrete random variable, remember we had the summations, so we can do the same thing. We simply say that the probability that x will take on values less than or equal to b or greater than a is simply going to be the sum of the PMF for all x's less than or equal to b, and we subtract off the sum of the PMFs of x for all values of x greater than or equal to, or less than or equal to a. So this may look, from our discussion a couple of slides ago, as this definition of the CDF. And that's exactly what it is. So we have the probability that the random variable x takes on a value that's less than or equal to b and greater than a is simply the CDF evaluated at b minus the CDF evaluated at a. Recalling that this value up here is actually the CDF, and if we want the range, we can use the PDF in this case between a and b. So that's our definition of our CDF when we go from minus infinity to the value. It gives us the CDF up to that point. So we can also find the probabilities in either way. Okay, we can find them either using the CDF or directly the PDF or PMF, the case may be. So at this point, I would refer you to example 3.2 in the textbook and also the accompanying video for example 3.2.